Assalamu alaikum. In this video we are going to learn about quantum teleportation and we will see how can we teleport a quantum state. Okay, so here what we understand by the definition is quantum teleportation is a mind-blowing basically quantum phenomena that allows the transfer of quantum information like the state of a particle from one location to another without physically moving the particle itself. It relies on quantum entanglement and classical communication. So today we are just going to learn a lot of stuffs today. Okay, so first of all, in the cartoons and others you might have seen, like, okay, there is a portal that comes up and via the portal we just pass some person, and yeah, it just goes from maybe one world to another or something like that. So what's happening, this person is basically not traveling the whole distance, right? Rather just passing through some portal, and it's something like teleportation. That's we're saying in quantum computing similar things do happen. And what it means is basically the goal is this qubit, it's not qubit, like the quantum state, this quantum state, there are like much more, like there are two more qubits. We are going to process it in that way that after a while we will just get it here. Okay, you see this quantum state is here, and we can exactly know which quantum state it is and something and so on. And this is basically what it is passed, but there are like much more qubits associated with here, and somehow we manage a process through which we can know, like, okay, which quantum state it is. Okay, so we are just passing it from here to here, right? Somehow there is a mechanism, so you can just consider these as the portal, right? This is the portal, so you can just consider this as a portal, and somehow it is passing from here to here. So this is what we are going to learn from here. So if you have seen my previous videos on how we need to process the quantum gates and so on, this video should be pretty much easy for you. Okay, but if you haven't done so, this should be slightly challenging for you, right? Because most of the videos I have seen, or most of the courses I have studied, like, it's not that beginner friendly. They are not there to make you understand, okay, which gate is applied on which qubit and so on. Okay, so we're just going to focus on that. So first of all, let's understand, or there is a situation which we have to understand, that is, we are assuming the quantum state and zero qubit, these values are kept to a person called Alice, or Alice, whatever you call, and there is another qubit which is kept to Bob. Okay, he had the value. Now what happens is, the rules are that Alice has this quantum state. Okay, and there is another thing, that Alice has this zero qubit and Bob has this zero qubit. What we have to do is we have to create an entanglement here, and you just don't need to know about it. If you just see this circuit, if we apply Hadamard and then not get, actually an entanglement is created. Now what are entanglements? If you don't know about it, entanglements are basically a way that one's result impacts another, or you can, if you know one qubit's result, then the state which is entangled with it, you will know the result about it, or you will know the result. Now what am I talking about it? Like, why, what is it? We'll see once I pass these two zero qubits through this. You will see the entanglement state, and then I will show that like how we can do that. Okay, there's no need to like bother about it. We just let's become like chilled. Let's chill about it and let's just see what happens. Okay, just keep it in mind that Alice has those two and Bob has just one. Okay, so let me just by A, and this is only B. Okay, great. Now let's start. So how are we going to start? First of all, let's start by doing In general, if you have seen my last video, you'll see like there are multiple ways to like apply gates on qubits. Okay, so if you can see this Hadamard, just focus on this, like this. Okay, if you just divide in like this, okay, or something like that. I am not able to write it or draw this properly, but sorry for that. But just see that for this quantum state, there is nothing applied in this portion. Nothing. Great. But when we go here, it's also again nothing. But here Hadamard gate. When there's nothing, we just go call it is identity matrix applied or something like that, because at the end everything is matrix. Hadamard, it has a matrix value, so we just call it like identity matrix is applied to this qubit and so on. Okay, you just don't need to bother about it. Once you learn much more, you will just know about it. But just focus on that, focus on this qubit. You see, we have to just remind our concepts. If you just seen last video, I'm just going to give this example, that is it should be q0, q1, and this should be q2, right? So q0, q1, and q2, right? This is going to be our examples. Now here is the point that in our videos I have just mentioned how I am or how the calculation is done, right? So you see that this Hadamard gate is applied on q0 or q0, sorry, q0, it's not q0, it's q0. So the thing is, how it should be, how this thing should be is somehow kind of, if you just look into this, after this state it should be is 0 and 0 applied, this head up, this is plus state. Okay, this is how it should look like, and this plus means is for q0, this 0 is for q1, and this is for q2. But I'm not going to make it complex for you. Just let's make it easier, and let's just divide it in such a manner that we can understand it easily. Okay, let's understand it easily. So first of all, what we are going to talk about is we're assuming that Alice has this 0 qubit and Bob has this 0 qubit, and these two are entangled. We're not assuming, but it's true, like it's entangled. And how do the entanglement states are created? Basically, one of the qubits are actually the Hadamard gets one of the qubit is put through a Hadamard gate and then a CNOT gate. So this is exactly what's happening here, right? So let's just pass it through. Just let's not bother about this one for now, because this is our target. We'll talk about it once we pass it. We come up here. Okay, let's just focus on this. Okay, we have 0 here. So if we just divide it right now here, okay, there's nothing here. So q on q0, Hadamard is applied. On q1, 0, there's nothing, no changes. So on this point, what will happen? We have 0, but once, so there is one principle. When 0 is passed through Hadamard gate, what happens? We get positive state. So what is this positive statements? It means the value should be it should be 1 by root 2, 0 plus 1, and okay, so this should be the state. Okay, great. This is how we create the superposition. Okay, from 0, like this is 0 qubit. From 0 qubit, if you want to create a superposition which is positive, so we just pass it through Hadamard gate. And for if we had 1, if we would have passed it through Hadamard gate, it would have become minus state, and minus becomes basically it is just minus out here, just 1 by root 2, 0 minus. Great. Okay, this is what it is. Now this is the concept part, nothing else. Now what happens is this 0 passes through nothing, so it's 0, but this 0 passes through Hadamard and becomes, basically after passing it through here, it becomes positive state. That means now in this point, like for example, not for example, this in this point here, like after passing it here in this meeting point, maybe 0. So in here it is 0, but here it is plus positive state, right? Great. That means in this position the value or the qubit state should be 0 and positive state. 0 from here and positive state from here. Now you may again ask, like, why did I write it in reverse order or something? This is how we do basically, because we want to mean it by like this. For this positive state is for the qubit 0, and this 0 is basically for qubit 1. Okay, this is how we do. If we would have qubit 2, we would have just written it here. Okay, something like that. Great, you just don't need to bother about it. If you are confused about this concept, please feel free to check out my last video in this series. Okay, I've just explained it properly. Okay, you can also see the comment sections that folks have understood the concepts very well. Okay, now this is great. Now we are just here. Great. 0 and positive state. Now the factor is this positive state, we can just elaborate it much more like this. Okay, we can just write it through 0, and then we can just write it like this. Great, we can just write it that, and then we can just multiply them, and if these quantum states are there or qubits are there, we can just multiply that, and it doesn't matter. An interesting factor about quantum gates are you can just reverse it and get the results back. In classical gates, you just don't get the result back. Okay, so what we can do right now is we can simply write it like this. I'm just going to explain it to you, no worries. Okay, just don't need to bother about it. Okay, something like that. Okay, so now just understand where this 0 is coming from. This 0 is basically this the leftmost one. Okay, great. And this 0 and this 1 are from the right part, or from this one. So these are for q0, and this one was for q1, and so you can understand these both of these 0 and 1 are basically q0, and this 0 and this 0 is for q1. Okay, so they are indicating the value of this one. Okay, so still after multiplication you can still identify which qubit's value it is. So that's great, right? Now okay, I just don't want to delete it. Maybe we can go to next page or another. We can talk about it, but now let's talk about where are we. We're still at this position, right? This is the value. Now we have to pass it through this NOT gate. Now you have to understand an important factor, that is how this NOT gate is working. Here you see this NOT gate, or C0 basically. I made a mistake. It's C0, control NOT. Okay, so this NOT gate is basically saying that okay, my control qubit should be 0 qubit and my target qubit should be qubit 1. This is what it is saying, because this black dot you are seeing, this is basically what the control qubit is, and this is where this sign means where the target qubit is. Now earlier we have just seen in the past video that how it works is basically if the control qubit is 1, this target qubit flips, because the NOT gate is applied on the qubit. But if the control qubit is 0, nothing is applied here because it remains the same. Okay, so now if I apply it here, if I just show you here, if we just applied C0 here, and if I just make you understand, like you see this is q0 and this the leftmost is q1, and I did mention that if the q0 this is the control. Okay, q0 is here, or control 1. If the q0 is 0, no changes made to q1 value, q1 qubit. If q0 value has 1, x gate is applied to qubit 1. That means it flips. Okay, now you see here the q0 value is 1. That means this is the q1, right? It will flip. Okay, it will flip, and this is what it is. But for here, this is q0, this is 0. That means nothing will change, so it will remain the same. That means after we go through c0, what will happen is we will have 1 value 2, then 0 0 plus 1 1. Okay, that's interesting, right? Because this was our q0 and this 0 was our q0. Now once like this q0 value was 1, basically you see this 0 has been flipped from 0 to 1. Now it is 1, right? It has turned from 1. But interestingly, still these two values do indicate the value of qubit 1. So after we gone through these states, we are currently here. Now you see in the qubit 2 we have some applications to be taken care of, right? But just keep it in mind, that is now this state is an entangled state. Now you may ask, like, what is entangled state? Just look into the case, just interestingly, just look into the thing, what it is. If I just write the value again, it should be 0 0 plus 1 1, right? Now you see, somehow assume that it is, obviously it's these two are q0, right? And these are q1, right? Somehow assume that we have managed to understand, just from here we have just managed to understand or managed to measure the value of q0 somehow. Okay, maybe we have passed through a gate, measurement gate, and we have got the value, that is, it is 1. Now you see that once the value is 1, the other qubit's value is 1, right? Exactly the same for 0 as well. If you just somehow measure the value of like 0 and you got 0, you can surely say that the other values are 0, and it is for just 2 qubits, and you can see like that. But in general, what can happen is there can be lots of qubits with it, like, okay, 1 2 3 4 5, 2 3 4 5, like that. Okay, and yeah, entangled states. So how are they entangled? Now you see, once state actually has impact on another, because once it is collapsed, which is basically is called when we measure it, and if we get the value, obviously we'll get the value 0, because this is a qubit state. Once we get the value 0, and you can surely say the other qubits will have the value 0 as well. That means it is making the process faster, right? Isn't it? Because we can now easily we just have to measure just one qubit, and we can easily say, oh, here we know what the other values are going to be. So it's very good, it's very great process to actually connect with the other qubits, make it entangle to reach a better target. Okay, great. Now why am I showing it? It's basically because if you just look into here, you see 0 0 1 1, because these are basically entangled states. Okay, great. So one of the rules for the quantum teleportation is these two 0 qubits should be entangled, and here it is. We have just explained that. Great. Now let me just tell you, like, okay, after this state, we are currently here. We have these two. We have this multiplication for these qubits, 2 qubits, and we have here this quantum state, which we can write it something like alpha 0 plus beta 1. Okay, and remember, this is exactly what we will try to find it here, and if you can find it here, exactly the quantum teleportation will be done. Okay, so now the thing is this, just understand from here, that is, in here we have some sort of multiplication state, which is this, and for this we had nothing, so it is exactly what it is here. That means now from here what we are going to do is we are just going to multiply all of these three, okay, because these two are already multiplied. We're just going to multiply with this. Okay, I'm just going to write it here so that you understand, can understand that, right? Okay, so what we have currently is 1 by root 2 0 0 plus 1 1 this step, and we also have another step which is 0 plus beta 1. We just have that. Now keep it in mind, that is that we have to multiply them, right? And this is for qubit 0 and these two basically, and these two are for qubit 1, and this is exactly the total thing is qubit 3. So if you multiply as we have learned earlier, we just put it through like this: 0 qubit 0 1 qubit 2 0 1 2, right, like that. So just let's put it here, like we have to multiply that, right? So just if you just do that, it's in general what we do is we basically do a cross product, something like that, and this is what it's going to happen. That is what we are going to do is 1 by root 2. Great, there's no problem with that, and 0 0, and there will be 0 0, no problem with that, but this is going to be multiplied with both of the thing. So there is going to be this. Let's just take this as common. So this 0 will be here and 1 1 will be here, and beta 1 0 0 will be here, plus beta 1 then 1 1 will be here. Great. Now okay, great. Now let's talk about what's happening and what happened. Like, let's just explain what happened here. So we just had this, we just multiplied that, and the main goal was these, like you see, these are from 0 0 1 1 0, like 0 0 1 1 1 1, yeah, and this 0 like alpha 0, this alpha portion, or beta 1 portion, beta 1 portion. Beta is the amplitude, but 0 is the qubit. It just multiplied, we just kept it there. Okay, there's nothing to worry about it. Okay, but the interesting factor is we just need to bother about, you just don't need to bother with the amplitude or other whatever it is, just bother about if we have the Q3 here or not. These are the Q3s. Okay, these are our Q3s now. Okay, as it's a cross product, what happens, like we have now like 4 values here in total, but yeah, this is how it works. And these middle ones are Q1 and oh sorry, it should be Q2, sorry, and middle ones are our Q1 and the rightmost are our Q0. Okay, great. Now after this we have to pass it through what? We have to pass it through C0. Interestingly, now why am I saying it? Because you see, this is the C0. Interestingly, it's saying that the control qubit is here, the qubit 2, but the target is qubit 1. Okay, that means whatever change we have to bring right now, it basically will depend on this qubit 2. Okay, let's just focus on this. Let's make the changes. So as I mentioned earlier, if the like again, let me just give you the example, 0 and 1, if you just pass it somehow through C0, what will happen? This 0 remains 0 and this 1 remains 1 as well, because this is something in general. What happens is, it looks like it is not C0, but in general we look it like that, or we draw it like that, and here we have okay, draw it like that. Okay, we just don't write C0 or whatever. So this circle is showing as the control qubit, and this is the target qubit. So you see, once the value is 0, nothing changed here. Once the value yeah, obviously this doesn't change, and again the value, the target value, it doesn't change as well. But let me make it better so that you understand, or you say, oh brother, you have been drawn it properly. Okay, let's just do it. Let's just focus on that. Okay, connect it like that. Okay, something like that. Okay, just focus on that. Now once the value changes from 0 to 1, now obviously if the value is 1, then it is 1 as well, because obviously there is no difference for the control one. But once for the target one, there is a X gate applied here. Okay, so for this one, this goes through a X gate, that means a NOT gate, which flips the value to 0. That means the value now should be the value now should be 0. Okay, so this is the principle for C NOT gate. Okay, if you still don't understand, please do check out my last video. Okay, now let's focus on that. As I mentioned, depending on the qubit 2, the value of qubit 1 will be changed. Okay, now let's focus on that, because qubit 2 is our control and qubit 1 is our target. Okay, now you see it's 0. That means just like that, when it was 0, this didn't change. So for example, let me just write it again so that I'm not going to explain it this time. Okay, 0, but this, yeah, when it was 0, this was exactly what it is. So for this is 0, this will remain 0, no problem. As it is 0, this will remain what it is, no problem. As it is 1, this should change, right? And this time this 0 should be flipped and it should become 1, right? It should become 1. And again, as it is 1, this should change and become 0. Great, I hope you understood it. So this time, now after this, we have 0 0 0 0 1 1 1 1 0, and we have 1 0 1. Great. Great. Now what happens? Now we have to apply Hadamard gate on what? That's again interesting. We have to apply Hadamard gate on qubit 2. Okay, so let's just focus on this Hadamard gate. As I mentioned earlier, again you see, when 0 is applied through Hadamard gate, we get plus state. And when 1 is applied through Hadamard gate, we get minus state. And we know what plus state means. It means 1 by root 2 and 0 plus 1. Okay, qubit, and it's basically superposition from qubit quantum state to superposition state. Yeah, that's it. So again, you have to understand that this Hadamard is applied on qubit 2, right? 0 1 2. You're just understanding it like that. So we have to focus on the qubit 2, which are the leftmost ones, 1 1 0 0, right? So let's just apply Hadamard. If we just apply it, we easily can understand this should be positive. I'm just giving, okay, I should not add this, rather than just write the positive one. Positive and the 0. This positive is for Q2. Okay, and this 0 should change and become, let me just remove these ones so that we can change it. And this should be positive. As it was 1, it should be minus. As it was 1, it should be minus, right? Great. Now things might be okay overwhelming for you. I do understand. I'm just going to write it, write the simplified version, no problem with that. Okay, let me just write it here, minus 0 1. Okay. Okay, great. Now this plus state is basically, in generally we know this plus is this one, 0 1 and 1 by root 2, right? So we can just simply write these down, but before that I just want to write these things here. Okay, I just want to write this one here so that we can explain it much better. That is, first of all, 1 by root 2, and we have alpha plus 0 0, and plus we have alpha plus 1 1, we have beta minus 1 0, we have beta minus 0 1. Great. These plus have their own meanings. Right now we're just going to write it down, but rather than this, just understand that these three, just you also have to, we just need to have this knowledge that what does this mean. This actually means that we have this, this and this. Okay, and we can just write them down in the multiplied version like this. Okay, no problem. That means when we want to like elaborate or write the mathematical version for the plus state, we can just write it like this, plus and then 0 0. Okay, no problem with that. Then like that, no problem, because we just don't want to divide them, no problem, right? We can just do that, minus and 1 0, and for this minus, sorry, minus should be minus, right? And 0 1, right? And then we just have the common of this. Okay, now the goal is basically this one, this one, this one and this one, just to divide them, right? Nothing more. Okay, let's just write it much more elaborately. Alpha, and this should be 1 by root 2, 0 plus 1, and oh sorry, 0 0. Okay, I'm just going to acknowledge them again, no problem, but let me just complete writing them so that you can understand them later on. 1 1, just write it downside. It should be 1 by root 2, 0 minus, and then 1 0 plus beta 1 by root 2, 0 minus 1, and then 0 1. Great. Now let me just, okay, these are the values for our plus states and these are the values for our minus states. Okay, exactly the same thing. Okay, and this is, and again you can just see these two are in the multiplied version, no problem with that. Now we can just multiply again, right? Because you see these are all 0 0 0 1 or something. So this is the portion, this is the last you can call it paradioc portion, whatever it is. So yeah, if we just take the common, or like 1 by root 2, if we just take the common, and you see in the, we have this right now, square version of this. But talking about these things, we have alpha and 0 0 0 0 0 0 plus alpha, because it's common here for all of these, it should be 1 0 0 1 0 0. Okay, I will explain again which is qubit 3, sorry, qubit 2, which is qubit 0, and which is qubit 1, no problem. But just let's just focus on the multiplication. Okay, one is done, this portion is done, this portion is done. Okay, now let's focus on the second portion, which is and this has been is in the common, so 0, it should be 0 1 1 alpha 1 1 1. Okay, after that this portion is done again. After that for the beta it should be 0 1 0, then minus beta 1 1 0, then again beta 0 0 1, then minus beta 1 0 1, right? That's it. So here we just have to look into is this is these are the qubit values for, basically these are qubit 2, and the middle ones are qubit 1, and the rightmost are qubit 0. Great. Now the thing is we can just take some commons, right? You see, you can just now understand like how can we take the common values and all. If we just we can just easily do that, right? Can't we? So what we can do right now is okay, we just look into this the 0 0. If we just take 0 0, where we have, you see, let me just take this one, 0 first two 0 0, we have 0 0, right? Great. We can do that for sure, but interestingly, what's our goal actually, right? Now why should we take common or whatever? Let's just focus on here. If you just look into here, that is, now after we pass through Hadamard gate, we we measure the value for qubit 1 and qubit 2. Okay, that means the qubit values are passed through here, and we do get the value, the quantum state just collapsed, and there is no quantum state then. Okay, this is what we have to keep it in mind, that here we have qubits 2 1 and 0, right? These two are going to be passed through measurement gates to get the exact value, to get 0 0 1 1 or something. So yeah, if you are not into quantum that much, it might be very much overwhelming for you, but now just let's focus on grouping the qubits based on the first two. Okay, then we'll understand what's happening, why did we do this. Okay, let's say you see 0 0 for q 0 0. If you just focus on doing that, we have just which is 2.5, no problem. But we have if you just do 0 0, if you just take common for 0 0, we can see that these two should be picked, right? Obviously we have seen these two, this and this whole thing should be picked. That means we can just write it like this: 0 plus midterm 1. Can't we? We can write that like this. Obviously we can do that. Okay, just focus on that, because if we just multiply them with this again, alpha 0, you can easily see that we will get alpha 0 0 0. And keep it in mind, that is, this is again qubit 0, this is qubit 1, this is qubit 2. Okay, keep it in mind. And again, if you just multiply this with this, you will get beta 0 0 1, and this is exactly what it is, right? So you can do that, no problem with that. So we can take common for this. Great. After that, what? After that, we're just looking for 0 0. So maybe 1 0. Let's go for 1 0. No problem. 1 0. We have this one 1 0. Let's use a different color so that you can understand. So 1 0, right? 1 0 1 0 1 0 1 0, right? Great. So let's just take the common, and yeah, we can just write it like that. Okay, no problem. And it should be for 1 0, it is 1 0, no problem. Then it's basically alpha 0, and this last state, last one, these are the things which we're considering for the common 1 0, and for beta it is b beta minus beta 1. Okay, great, no problem. If you just multiply, we should get alpha 1 0 0 1 0 0, and if you just multiply with this, we'll get beta 1 0 1 1 0 1. Great, exactly what it is. Now again, we're done with this too. Now 1 0, so 0 1, let's focus on 0 1. 0 1 is here, 0 1 is here. Okay, so let's just focus on 0 1. Great, then if we just take this two based on that, so then alpha and 1 does remain 1, no problem. Then for this we have 0 1 plus we have 0 1, then beta and sorry for that, you might not understand that. So beta and these 0 remains, right, because these are the portion for the common, so 0 remains. Again, if we just multiply, we get alpha 0 1 1, so 0 1 1. Great, if we just multiply, we should get beta 0 1 0, so beta 0 1 0. Great, so it's done properly. So now remains what remains is this 1 1, so this is 1 and another should be here 1. Okay, so if we just take the common 1 1, and so it should be alpha, and remaining portion is this one 1, and for this should be common, so the remaining portion should be, you see, minus beta and this 0. Great, isn't it? Done. So yeah, we have gone through a lot and we have just learned about these things, right? And great. Now what happens? What are we bothered about much more? The thing we are bothered about right now is you can understand that these are the state multiplications for basically qubit 2 and qubit 1, qubit 2 and qubit 1, qubit 2 and qubit 1, and this is for qubit 2 and qubit 1. So if you just look into here, what these signs basically mean measurement. Okay, you can call it like this, m, no problem. So these two qubits are passed through measurements, and these you see double lines, that means classical values, because once quantum states are passed through measurement, we do get classical values. Okay, great. So now obviously that means now these are basically 0 0, which are basically quantum states. Now it will be passed through, you see what happens if we have 0 0, it passes through measurement gate, it basically becomes 0 0. That's it, that's what I am talking about. Okay, because these are quantum states, these are classical. And how do we understand? In general, we do add this bracket in quantum states, but classical we just don't add that, and that's it. That means if we pass this value through the measurements, we'll get 0 0. If we pass these through measurement, we'll get 1 0, we'll get 0 1, we'll get 1 1. Okay, now let's create a table. Okay, because you'll see what's happening. Okay, great. Now let's create not exactly table, but like that. Okay, now if we have q2 q1, the classical value, obviously let me just write classical, this thing, and this should be our q0, and we have to take some measurements or actions to get this one. That means alpha 0 plus beta 1. Okay, I'm just going to write it here so that you will see what's happening. Alpha 0 plus beta 1. Okay, so our goal is to get somehow our goal is to get the q0 somehow like this. Okay, let's just focus on that. So for the first time, once we have 0 0, once it goes through measurement, it is 0 0. And if it is 0 0, now you understand, you see, when the classical value is 0 0, or q1 q2 value, the multiplication of those values are 0 0, you can see that this value, which is q3, is alpha 0 plus beta 1. Great. Now you see, if you just look into the right portion, you see this is exactly what we were looking for, right? That means when the classical value, or when the q1 q2 value is 0 0 exactly, we are getting what we wanted. We have been looking for this for the whole time. We have got it. We've got this state from here. It was in q2. We have somehow got it in the q1, isn't it? Sorry, q0, right? Isn't it awesome? This is teleportation, right? Somehow we have made such a process that in the q0 we have just got this q, the value in q2. Okay, now when the value is when these the measurement value is 1 0, because yeah, obviously, let me just write it like this so that you understand better. 0 0 goes through measurement and we get this. Okay, so then it should be 1 0, it goes through measurement and we get this value, which is 1 0. Now you can look into this one. We have to write it here, 0 minus beta 1. Interesting. Now if we just look into this, what can we see here? What we can see is we should apply z gate here. Okay, which we should apply, yeah, which should be control z, right? Yeah, we should be applying these gates. Yeah, control z. Okay, so what does it mean? That means is, if we look into here, what happens is basically, here you see this value is q2, right? And this is obviously our q0, right? That means when the value of q2 is going to be 0, okay, 0, so obviously nothing happens in general. But when the value for this q2 is 1, z gate is applied here, and when z gate is applied here, we have to keep it in mind, that is how z gate works is, if we just pass 0 through z gate, it is 0. If we pass 1 through z, we get minus 1, okay, this is minus 1. Okay, okay, great. That means, so yeah, that's it. So the thing is, what happens, so you see, like, why did we write z? Because basically this is q0, right? And if you just look into here, if we just look into here, we have 1 0 in general, right? So what are you bothered about? Let's just focus on this. Let me just remove it. Because once you just go through this video, it should be explained properly, right? You see, as I mentioned, if the q2 value is 1, if we just follow the control z, that the z is applied the whole gate. Okay, the z will be applied here if you just follow this architecture, because obviously this is how control z works, and this is exactly how the control not or c naught works. Okay, because depending on the actually the control one, the target value, like the gate on the target is applied and something like that. Because when we talked about c naught, what happened? Because when the value is 1, there was an x gate applied on this qubit, isn't it? When the value was here 1, the x gate was applied here. Exactly the same thing. When the value is 1 here, the z gate is applied on the qubit. Okay, So if you look into here, again you have to keep it in mind, this indicates q2, okay, and this indicates q1. So when the value is 1 for q2, obviously what happens, z gate is applied here. And I mentioned you again, that means when 0, now what happens here, what happens basically, each and every value goes through the z, the z gate. What happens, you just see, we'll just look into that. That means after this alpha, and we have z0 and beta, sorry, z1 or something, and it just passes through z0 or something. How we can visualize it is like this. In classical computing, we also talked about it, like maybe we have x something like 0, we can just call it like 1, like that, right? So when we have z and the qubit 0, we can just call it okay 0. When we have z1, we just have the value -1. This is the principle, obviously, okay, we just learned it earlier, and you can just google it, no issues with that. So what happens, what should happen, what should be here, it should be 0, no problem with that, exactly it should be. So alpha 0 for the for this one, beta 1, when passes through z, it becomes -1. That means minus minus, it should multiply and becomes plus, and it should be 1. Great. Now you see, this is exactly what we're looking for. Again, we have got what we were looking for. Great. Now let's look for another thing, which is 0 1. When we do have the value 0 1, 0 1, when it passes through measurement, we get 0 1. Great. When we do have 0 1, you see the value is 1 plus beta 0. Now interestingly, what the architecture, we can see the what architecture says, but we can again look into what our desired state is. You see, the desired is alpha 0 plus beta 1, 1 qubit, but we have alpha 1 and beta 0. Great, interesting factor. So this is not what we want, right? We want the result to be flipped, isn't it? Right? We want the result to be flipped, right? That means we want some sort of NOT gate applied on this. If you just look into the architecture, you can see for the value, and here you can see that the classical value, whatever we have, we can just apply the NOT gate out here. Okay. Okay. So you see the q1 here, just q1, obviously that one. So when the value is q, or you can just assume it something like, maybe if we would have applied a c0 here, we can exactly assume it like that, because this is q1, this is q2. When the value is 1, we can apply the x gate out here, and when we apply an x gate, what happens, you see, when we pass 1 qubit through x, the value should flip and become 0. When you pass through this, value should become 0 to 1, right? Now you see, we have exactly 0 1 and other, so we are successful again. Now let's talk about the last thing, which is 1 1. When we have this one and we measure this, pass it through measurement gate, it is 1 1. And for 1 1, what we have is this one, which is alpha 1 minus beta 0. And this time, you see, we applied both of the gates, which is the same thing, like control Z and control X, exactly like that. Because you see, this time what happened, and this whole of the things, like in the later we can also talk about this 0 0 again, we'll talk about it. What happens, you see, for q, which is 1, and this is for q2, right? For q1, as the value is 1, there should be some sort of what applied, as I mentioned, x gate should be applied. When the x gate is applied, what should be the value? 1 should be 0 minus 1. Great. Once this is done, again when the value for this q2 is 1, the control z gate applies, because the rules are actually same for everyone. You see, we'll just talk about it later on, just after the calculation. Once this is done, we'll just apply the, once it is 1, we just apply the z gate over the whole thing. So once it is done, it should be 0 and it should be plus beta 1. Great, done. You see, this is exactly what we were looking for. We are again successful. We have successfully actually got the value. Now let me just remove these things. I hope you understood this. Sorry, I just mistakenly removed the value. Yeah, my bad. And remove this one. Sorry for that. Okay, we're done. It should be obviously 1 0. Great. Now you see, whatever we have gone through, like as it was 0 0, nothing was applied, because obviously when does this thing work? Because when if you just look into here, that's it, we have just applied control z, cz, cz, and we just applied c naught. That's it. So depending on the values of these two qubits, we have just applied x or z, and x and z is basically control z and control x or control naught. What is exactly what it is. So if you just remove these things, we just can see that whatever we have the value in q1, q0, depending on that, we can just apply this cz and cx or c naught, and we will get this value, right? Isn't it? If you just look into this 0 0, exactly what it is. When we had 0 0, obviously none of the cz or c naught is triggered, and that means it doesn't go through cz or c naught or cx, and this is what exactly the value should be. And yeah, we are getting the exact value, no problem with that. But when we pass this value through those cz and c naught, you see the for the q1, obviously nothing get triggers, but for this q2, this control z get triggers, and it is getting applied. And for this thing, obviously control x is triggered and it works, but it doesn't trigger. But for this, both of the things like control x and control z get triggers, and we get the value. That means this is the architecture, quantum teleportation architecture, which can give us what the value we had in q2. Okay, you see, after the whole process, in the initial process, the qubit 0 had the value 0 qubit. Okay, you see the qubit 0 had the value 0 qubit, but after the whole process, the qubit 0 can actually teleport this value somehow here, and there was some sort of process like this measurement, and it all again helped us get this value. Now whatever value we have, however we do manipulate, whatever it is, now we can easily understand. That means whatever we have in q2, we can easily get it in q0. This is the teleportation. This is the process we have gone through, and this is what it is. So we have successfully understood what is quantum teleportation and how it works. So yeah, that's a very interesting topic, and if you have any questions, feel free to ask me. I do understand if I was unable to showcase anything or made any mistake, sorry for that. And if you have understood the concept, feel free to share it with your friends. But if you haven't, feel free to ask me the question. I will try my best to make another video if you haven't understood the concepts. But yeah, I hope you have taken or you have given enough time to understand the concept, and feel free to understand the theoretical concept from Google and another social media or whatever it is. It can be social media, it can be browser, it can be AI, whatever it is. but this is the theoretical concept, right? So yeah, thank you so much for watching this video, and if you have any question, feel free to add this in the comment section. And thank you so much. See you in the next video.